Okay, good day everyone. I'm Masato Tsutsumi from Waseda University. Today I'm going to be presenting my research on benchmarking zkVMs, efficiency, bottlenecks, and best practices. Let me begin by explaining the fundamental concept of zkVMs. A zkVM is a technology that proves the correct execution of arbitrary computer programs. The operation of zkVMs consists of two steps. For example, if you have a program that calculates nth Fibonacci number, we first executed it with input n, and then produces the execution trace. This execution trace includes like memory value and opcode for each instruction step of the program. Next, we generate a proof based on this trace. The verifier can then verify the proof, for instance, that the 10th Fibonacci is equal to 55 without having to re-execute it themselves. During the proof generation, the zkVM proves the state transition of the VM at each execution step using snarks. When a program is compiled, it expands into instructions such as add, load, store, and so on. When the ith instruction is executed, the VM's memory, register, and program counter value transition to the next state. And to prove the state transition, three basic proofs are required. First, instruction encoding proof, proving the encoding from binary to instruction is correct. Second, read-write memory consistency proof, proving the value purportedly returned by any read operation is equal to the value most recently written to the appropriate memory cell. And third, instruction proof, proving that the instruction execution results are correct. By repeating these proofs for each execution step, we guarantee the validity of the final execution result. A major application of zkVMs is scaling Ethereum smart contract. Ethereum validators can update the Ethereum state by verifying the proof instead of re-executing the blocks on their EVMs. And this allows transaction fees to remain constant regardless of any program complexity. And one thing to note here is that zkVM is not necessarily designed for privacy protection. Their primary purpose is to make computation results efficiently verifiable through snarks. Currently, many zkVMs claims to be the fastest, but they actually measured under different conditions, making it difficult to compare objectively. And systems touted as the fastest often has limitations such as enormous memory consumptions or only works for specific programs. Therefore, we built a standardized benchmark framework to comprehensively compare and analyze multiple implementations across various evaluations and target programs. There is significant value in presenting standard benchmarks from a neutral community like zkproof. A familiar example is large language models. They usually cite benchmark scores as the evidence of performance when releasing new models. Furthermore, our research identified the CPU and memory bottlenecks for each project. And we also estimated the best practices for leveraging existing zkVMs. We compared mainly 7 projects, SP1, RISC-0, and Jolt for both CPU and GPU implementation, and OpenVM, zkM, Nexus, NovaNet for only CPU, as they don't yet have GPU implementation, and Seno for only parallel performance for 100K Fibonacci, as they don't yet have SDKs. So let me introduce some zkVM implementation briefly. RISC-0 SP1 OpenVM zkVM adopts similar approaches. Proof generation involves 4 steps: execution trace segmentation and proving, proof aggregation, and stack to snark. And the approach from execution trace segmentation to proof aggregation, like a parallel ways, called continuation. And common feature is the adoption of fly stack-based proof systems. Use 32-bit fields to efficiently generate proofs. Seno also uses continuation, and the major difference is its adoption of GKR proof system. And Jolt currently doesn't support continuation. And Jolt adopts the lasso lookup arguments, which looks up the results from the pre-executed result table instead of executing instructions through circuits. And Nexus currently uses Store, fly stack-based systems produced by Stackware, but originally adopts Nova-based folding schemes. And NovaNet uses both the folding scheme and Nebular, which provides efficient memory checking argument and switchboard technology. As shown in this table, the fly stack system is the most popular right now, and all projects except Jolt supports continuation. And another important technique is precompiles, which allows certain operations like hash functions or signatures to be proven by custom circuits much more efficiently than compiling them to ISS. And there are variations in precompile support, and this support can significantly impact the prover time efficiency. And the rest of my presentation proceeds as follows. For our comparison, we run benchmarks on the AWS EC2 instances equipped by 64V CPUs, 256 GB RAM, and 24 GB GPU memory. And we compared the 7 projects mentioned earlier. And test programs included calculating the 100K Fibonacci number and SHA-2 2048, and ECDSA verification on K256, and EVM execution on a simple 100 ETH transfer transactions. And evaluations are primarily divided into time efficiency and memory efficiency. For time efficiency, we first compared prover time. Next, we evaluated program generalizability based on whether proof generation could be completed within 1 minute. Then we compared increases in prover time when changing input size. And finally, we compared efficiency improvements when changing the number of CPU cores. And for memory efficiency, we compared peak memory usage. And the benchmark programs are publicly available on GitHub, allowing anyone to reproduce our results. And when a program is executed, each zkVM calculates cycle count to estimate the proving cost. And cycle count is calculated based on the trace, following some rules, such as 1 cycle counts for addition instructions and 4 cycle counts for memory access instructions. But these rules are a little bit different among projects. And surprisingly, we observed variations among projects in cycle counts, even for the same projects. For example, for the 100K Fibonacci program, SP1 cycle counts was only 600K. And for risk zero, the cycle counts was about 2.4 million. Such large differences suggest that the number of cycles are reduced through the use of precompiles or some optimization techniques. So moving on to comparisons, this graph shows proof generation time for 100K Fibonacci program by CPUs. And OpenVM was the fastest, was only 11 seconds in prover time. And with SP1 and Jolt showing the next best efficiency. And that graph includes the 3 other programs alongside Fibonacci, from top to bottom, Fibonacci, SHA-2, and ECDS and ETH transfer. And first, even with the similar cycle counts, prover times differ. SP1 and RISC-0 both have 5 million cycles for each transfer. Program, but prover time was vastly different in 46 seconds and 321 seconds, respectively. And OpenVM was the most efficient across all 4 programs. And for SHA-2 programs, Jolt was also very fast at just 5 seconds. And next, this graph shows the results for GPU performance for SP1 and RISC-0 and Jolt. And SP1 and RISC-0 were much more efficient than their CPU implementations. And Jolt shows little difference as they only support GPU acceleration for some components. And notably, SP1 generated proof for EVM execution for only 4.7 seconds. And while some more complex contract execution need to be compared, achieving to 12-second real-time proving is promising for practical applications. So overall, SP1's GPU was the fastest, and followed by RISC-0's GPU and OpenVM's CPU. And at the time of the paper submission, we had compared only 5 projects and 2 programs, Fibonacci and matrix operations. And following zkProof 7 reviews, we expanded to 7 projects and also added programs like SHA-2 ECDSA verification and AVM executions, and which are much closer to real-world use cases. And the NovaNet team made significant contributions, such as including supporting EVM executions, and we greatly appreciate their helps. And this table visualizes whether proof generation could be completed within 1 minute. And SP1, RISC-0, and OpenVM cleared this threshold for all programs, demonstrating sufficient program generalizability. And zkVM cleared 1, and Jolt cleared 2 of these thresholds. And this graph shows how proof generation time increases as Fibonacci's input size changes from 10, 100,000, 10,000, 100,000. And Nexus and NovaNet became unmeasurable after a certain point due to accessible time requirements. And most implementations shows super linear increases in proof time with input size n. This means the linear time increases with the input with the cycle counts. And RISC-0 and Jolt And zkM showed high increase rate, while SP1 had the lowest rate, showcasing its efficiency for large-scale programs. To measure the parallel performance, we measured the proof generation time with varying the number of CPU cores from 2, 4, 8, and 12. And the left shows the result for 1,000 Fibonacci program, and the right shows the for 100K Fibonacci program. And here we compare only for SP1 and Nexus and Seno. The comparisons for other projects remain for future work. And we observed efficiency improvement of up to 8x. And larger programs appear to benefit more from increased core counts. However, there are limits to efficiency gains from parallelization. In both programs, using more than 8 cores resulted in either small improvements or even decreased efficiency. And this occurs when parallel processing overhead exceeds gains. Therefore, it's important to select an appropriate core count based on program scale. Regarding the comparison on peak memory usage for 100K Fibonacci by CPU, notable is zkMs are large 83 gigabyte peak memory usage. Meanwhile, Nexus and Novanet maintain constant memory usage even with increasing input size. However, as we saw earlier, they trade this for significantly lower time efficiency. And this is for GPU's peak memory usage performance. And SP1 and RISC-0 achieved much lower memory usage during GPUs. However, they used around 24 GPU memory instead. And Jolt showed real difference memory efficiency between CPU and GPU. So overall, RISC-0's GPU and SP1's GPU were the most memory efficient, and while Nexus and Novanet were most efficient by CPUs. However, when measuring it on ECDC verification locally, we observed even higher peak memory usage. While Novanet and Nexus consistently maintain low values, zkM and Jolt reached about 110 gigabytes, and others reached about 30 to 50 gigabytes. We summarized in this table the most time-consuming processes as CPU bottlenecks and the processes running during memory peaks as memory bottlenecks. For example, Jolt's CPU bottlenecks were Lasso's Samsek protocol and Spartan, and polynomial generation in Lasso lookup table was the memory bottlenecks. And this bottleneck analysis was based on the visualizing frame graph. And please contact us if you'd like to know more about this analysis. Here are the guidelines for best zkVM selection and specification based on resources and requirements. For zkVM selection criteria, SP1, RISC-0, and OpenVM seem to be good for general purpose use cases. And it's recommended to use zkVMs that supports the precompiles need for your specific programs. And it's recommended to measure the most efficient core currents for proof generation. And for GPU specifications, 24 GPU memory is required for running SP1 JOT, SP1 RISC-0. And for memory specifications, at least 32 gigabyte RAM is recommended for general purposes, and using JOT and zkVM may require 120 gigabyte RAM or more in some cases. That concludes our research. Future challenges for our benchmark framework include more detailed bottleneck analysis and support additional new zkVM projects like Waseda and Pico, as well as the latest version of current projects, and support for programs with wider applications such as float and matrix operations, and complete comparisons for processing efficiency. We will continue working on these challenges for further enhancing the stability of our zkVM benchmark framework. And of course, we are so welcome for your contributions. Please flag up pull requests or issues to our repository. That's it. Thank you for your attention.
So I have one quick question. So one important thing that you highlighted is obviously the memory consistency checks. Have you noticed, or are you able to evaluate, let's say you take two different sorting algorithms, you run them on the zkVM, and one of them has a random memory access pattern and one of them has sequential memory access patterns. Like, could you tell ahead of time like how much overhead that would add, particularly for zkVMs that have continuations and where you'd have to enforce consistency checks at the boundaries of each chunk that you would then prove in parallel?
Yeah, actually, I don't have the answer for that, but yeah, I wanted to more detailed, analysis on the bottlenecks, but I want to do it in the future.
Perfect, thank you.
Do you have plans to extend the set of benchmarks to some of the things that have been considered in previous zkProof conferences that represent sort of more realistic cryptographic protocols? I've noticed that the benchmarks are basically only checking a deterministic function for particular inputs, which in principle it's either true or false, so you can optimize it down to nothing. Whereas if you have a cryptographic protocol that you're trying to implement based on public inputs, then that can't be optimized down to nothing. So the things that we were talking about were like Merkle tree inclusion proofs and so on. Do you have any plans for that?
Sorry, what is?
So there's in previous zkProof workshops, we've discussed various protocols and benchmarks that would be useful in practice, so beyond just repeating Jadu or repeating Fibonacci or whatever. Do you have plans to go back and look at those suggested benchmarks and implement them?
Yeah, I think the most use cases for zkVM is proving the Ethereum blocks. So I think, yeah, the performance for proving prover time for proving Ethereum blocks is one matrix, as the ETH proofs are working on that. Yeah, and also, yeah, some many zkVM projects are working on implementing zkMLs, like proving machine learning by zks. So I think such operations like matrix multiplications or activation functions or any other, machine learning operations should be compared.
Yeah, I mean, speaking as a cryptographer and protocol designer, benchmarks like that aren't useful to me because I don't care about machine learning and I don't really care about EVMs, but I'm trying to get an idea of sort of how particular building blocks that are very commonly used in protocols behave on the various platforms.
So I think maybe a question would be, how easy would it be for someone to take your benchmark setup and to try and add a program to that?
Yeah. So I asking setting the
So if
benchmark
someone
on-
wanted to use your benchmark setup, but to benchmark something that you haven't benchmarked yet,
yeah.
how easy would it be for them to do this? And just submit a pull request that says, you know, I've added a couple benchmarks.
Yes. Actually, setting the benchmark is so difficult because it's running on Linux systems and should install so many tool chains for running so many projects. Yeah, should be make it so easy. But I have prepared our bash script for installing those tool chain as one command for now, but actually should be maintained. Yeah.
Okay. Maybe future work then.
Yeah.
Thank you.
Thank you.
Any other questions?
Thanks for the work. Do you plan also to compare and bench zkEVMs, which I understand is a little bit difficult to run them out of the box, let me say, but indeed it could be useful?
Yeah, not currently supporting zkEVM projects. I think it is totally different to compare. Of course, zkEVM are much more efficient than zkVM projects. Yeah, but I think I will consider to support these zkVM projects.
Thanks.
Okay, thank you. Great talk.
Thank you.